In VR/AR rendering, it has been widely assumed that the viewpoint of the eye is the rotational center of the eye. However, the correct viewpoint is actually around the front nodal point of the eye. This causes a small parallax only with the eye rotation, called ocular parallax. Here's the comparison between conventional rendering and ocular parallax rendering. With ocular parallax, the rendered point on the display moves according to the eye rotation to keep the 3D position of a virtual point stable. By contrast, the conventional rendering does not, resulting in an apparent shift of the virtual point and image distortion. Ocular parallax rendering may improve several VR/AR experiences, such as improved depth and size perception and realistic viewing. Conrad et al. Studied the ocular parallax rendering on head-mounted displays attached with a commercial eye tracker. As shown in the right video, the scene moves according to eye rotation with ocular parallax rendering. This study revealed a positive effect on relative depth perception by enabling ocular parallax rendering. However, this system had a large system latency of over 20 milliseconds. Previous research revealed that the acceptable visual latency according to the user's motion generally has a severe value. The low-latency projection mapping was previously proposed. It was evaluated that such a sticky projection mapping can be realized under the small system latency. Therefore, to examine the ocular parallax rendering effect in detail, we built a low-latency ocular parallax rendering system from scratch. Using this system, we investigated the latency requirements for ocular parallax rendering. Furthermore, we also examined the effect of ocular parallax rendering under free viewing for binocular and monocular depth perception tasks. This is a demonstration video of our low-latency ocular parallax rendering system, whose frequency is 360 Hz, and system delay is 4.832 milliseconds. Eye tracking is built from scratch since the front nodal point is unavailable in most commercial high-speed eye trackers. The anaglyph binocular parallax images are rendered according to the viewpoint change. The ocular parallax rendering exhibits motion, while the conventional rendering does not. The system performance was evaluated, and the spatial accuracy of eye tracking was confirmed to be extremely high. The system latency was evaluated as low as 4.83 milliseconds, which is much smaller than head-mounted displays. Then, using the proposed low-latency system, we evaluated the latency requirements for ocular parallax rendering to achieve perceptually stable virtual scene rendering. The acceptable latency of perceptually stable ocular parallax rendering was evaluated under monocular and binocular vision. Here are the result graphs of acceptable latency. In monocular viewing, the acceptable latency at 2 and 3 diopters was already less than the system minimum latency of 4.832 milliseconds. The latency requirements were less severe in binocular viewing. Interestingly, sensitivity to latency depended on motion direction, suggesting the ability of the visual system to utilize extraretinal signals. Next, we investigated the effect of ocular parallax rendering under free viewing for both binocular and monocular depth perception tasks. First, for the binocular task, we investigated whether ocular parallax rendering facilitates binocular fusion, using the random dot stereogram. If the binocular fusion was successfully completed, the elliptic point group appeared in front of the display. Here is the result of the proportion of successful binocular fusion. We found a significant improvement with ocular parallax rendering compared to conventional rendering. The improvement was observed even when the latency was relatively large and if the motion direction was inconsistent with that of eye movements. As for the monocular viewing task, we employed the experiment of ordinal depth judgment of two partially overlapping textures, where the available depth cues were limited to dynamic occlusion due to ocular parallax. This task design follows the previous experiment performed by Conrad et al. As a result, reliable depth judgments were only achieved under the large latency condition. This suggests that awareness of stimulus motion is necessary to judge depth under monocular viewing. Here is the conclusion. Thanks for watching our video.